Okay, let's go ahead and get started with section 1.4. In this section, we will be looking at two additional case studies in which we use the two alternative forced choice models that we've talked about previously. Okay, let's go ahead and get started. The first example that we're going to look at is the gender discrimination example. This is a fictitious example, but it is based loosely on a gender discrimination lawsuit filed against Walmart. Walmart was accused of discrimination against women in terms of salary and promotion opportunities. Now, often for large corporations, a company creates a pool of employees that are eligible for promotion to a managerial position. This is necessary as additional training is often necessary before one can become a manager. Employees in the management pool have completed this training and are ready to be promoted to a management position. For the sake of discussion, let us suppose that the management pool for a particular company is large and contains 60% female and 40% male. From this pool, 20 new managers were selected, 9 of which were female and 11 male. The question of interest here is there evidence of gender discrimination against females in this company for those chosen for a management position? Okay, the investigative goal. Given that 20 individuals were promoted to a managerial position within this company, and knowledge that 60% of the potential management pool was female, we can compute the expected number of females that should have been promoted under a no discrimination situation. The relevant quantities for our simulation model are as follows. The number of trials, which here simply represents the number of people promoted, is going to be 20. And the second quantity that needs to be identified is the chance of a woman being promoted under a no discrimination situation. In other words, an all things fair situation. The management pool contains 60% female and 40% male, so this chance is simply 60%. To compute the expected number of women to be promoted under a no discrimination situation, we would simply multiply the 20, which is the number of people promoted, by the 60%, and we get a value of 12. So 12 represents the expected number of women to be promoted when no discrimination was taking place. Recall from the outcome of the study, we had 9 females that were promoted. So the question is whether or not that is enough evidence to say gender discrimination is taking place. Expected value is 12. We actually observed only 9. And is that enough evidence to suggest discrimination taking place? The following schematic can be used for the setup of our simulation model. Let's briefly talk about the various values on this schematic. The lowest possible value in our simulation study would be 0. 0 would certainly indicate that we have discrimination against women. If we evaluate the last 20 hires and none of them were female, then that would suggest discrimination against women. On the other hand, the highest possible value in our number line would be 20. Again, if all 20 of the individuals were female, that would actually suggest discrimination against men. So if we evaluate the last 20 hires and all 20 of those were women, that would indicate discrimination against men. The quantity that we're going to track throughout the simulation is going to be the number of women promoted. So we'll use that as our label on our number line. The center of the pyramid is simply the expected value, and that is again computed as 20 times 0.6. So that's where that pyramid is going to be centered. The study outcome, the value that we actually obtained in our study, is 9 for this example. We had 9 women that were promoted and 11 men that were promoted. Now, which side of the distribution do we care about? Well, we care about the left side, or the left edge of the distribution. We we care about the left side because the question of interest was asked, was asking whether or not we had enough evidence for discrimination against women. And that is indicated on the left side of this distribution. Now the goal here in this simulation is going to be to determine whether or not 9 is an unusual outcome against a no discrimination situation. The no discrimination situation is represented by our reference distribution. However, I do not know how wide or how skinny my reference distribution is. If my reference distribution looks like this light gray version here, then 9 would be considered an outlier. On the other hand, if the reference distribution is indicated with the darker gray pyramid, then 9 would not be considered an outlier or would not be considered unusual. So what the simulation study does is it identifies where that reference distribution is at, and more importantly, how much inherent variation exists in that reference distribution. And we use that to evaluate whether or not our study outcome is an outlier. So let's proceed with generating that reference distribution. We will obtain the reference distribution using the app that we presented in the previous section. Before doing that, let's just talk a minute about the possible outcomes and their associated probabilities. So if we were going to use the 2AFC app, that app explicitly requires us to identify what the two outcomes are. The two outcomes in this study are women and men. The probability associated with women is going to be 60%, and the probability associated with men is going to be 40%. Again, the 60% represents the chance that a woman is going to be promoted under a situation of no discrimination. The sample size here is 20, because that's the number of promotions that is being investigated here. Now when I click Run Simulation, I obtain a single outcome from the simulation. So how does this compare against the reference distribution app? The reference distribution app requires us to identify the probability of a success. Here, that probability of success is going to be identified as that 60%. I'm going to indicate that a success is a woman being promoted. So that's what I'm going to use for a probability of success here. The sample size is simply going to be 20, just like it was in the 2AFC app. The number of samples, I have set that to be 100. This is the total number of repeated outcomes that will be obtained from the simulation model. So by putting 100 here in the number of samples, I should have 100 different simulated outcomes on my plot. And that's what we have below. So here is the outcomes from the reference distribution app. And we can see that this pyramid is centered at about 12. This distribution is centered about 12. And then it moves down and from both sides of that. Again, it has that pyramid shape. Let's go ahead and answer some questions about that reference distribution. Number 1, what is the lowest possible value from this simulation? Note that I asked what the lowest possible value was. Okay? Not which is the lowest that I obtained, but what is the lowest possible value that I could get? The answer to that is 0. Okay, so even though this number line doesn't extend all the way down to 0, it is possible to get a 0 for number of women promoted. So the lowest possible value is going to be 0, and again this indicates discrimination against women. The highest possible value that we could have obtained from our simulation is going to be 20. Again, it doesn't look like I got one past 17 here, but this number line actually extends all the way up to 20. So the highest possible value is going to be 20, and this indicates discrimination against men. Next question. This reference distribution is centered around 12. Should it be? Yes. 12 should be the center of the distribution, as this is the expected value. The next question. The generic label on this plot is just number of successes. So if we go back up and look at this plot, we can see that it's generically labeled number of successes. A much better label would be the number of women promoted. So one thing that the reference distribution app does not do is allow us to provide a specific label on our dot plot. Okay, so it just generically labels that or identifies that as number of successes. So a better label would be number of women promoted. Okay, again, a success was identified as a woman being promoted. Next question. Which of the following is most correct regarding the dots obtained from our simulation model? Okay, so it's been a little bit since we've looked at this. A, these dots were generated under a situation of discrimination. B, these dots were generated under a situation of no discrimination. Or C, no assumptions were made when these dots were generated. Making assumptions like this, okay, will bias our investigation. Okay, the correct answer here is going to be B. All right. Again, we build these distributions, okay? We build these distributions under a no discrimination situation, or we build these distributions under a fair situation. Okay. Now, this gets a little confusing because we're trying to evaluate whether or not discrimination was taking place. But recall, what we do is we take the outcome from our study, and we just set it aside for a moment, and we build a reference distribution under no discrimination, and then we'll bring our study outcome back in and try to determine whether or not it's an outlier against a no discrimination situation. Okay, let's apply the outlier rule to this example. The outlier rule requires one to identify the 5% of the distribution that we would consider unlikely. In this investigation, of interest is the bottom 5% of the distribution because the research question or the question of interest is concerned with too few females being selected for promotion. So let's consider some possible cutoff values from our distribution up above. Recall from our distribution up above that the lowest values that I obtained in my simulation were 6. Okay. We could set the cutoff value to be 5, but that cutoff value is going to be too conservative. So if I set my cutoff value to be 5, we could quickly identify or calculate the proportion of dots that lie at this cutoff value or below. There weren't any down there. So that calculation would simply be 0 divided by 100 or 0. Using this cutoff value would be too conservative. The implication of using a cutoff that is too conservative is that in cases where discrimination was indeed taking place, our model would not appropriately identify the discrimination. So if we put that cutoff value too low, we're not going to be able to identify when discrimination is taking place. We could choose a cutoff value of 6. If we choose a cutoff value of 6, let's go back up to our pyramid a minute. If I choose a cutoff value of 6, I can see that I have 2 dots at 6 or anything less than 6. So the proportion of dots as extreme or more extreme than 6 would simply be 2 divided by 100. This is certainly less conservative than 5, but it is somewhat under the widely accepted value of 5%. If we move our cutoff value up to 7, let's go back up to the pyramid and look at that a moment. If we put the cutoff value here at 7, anything less than 7, okay, 7 or anything less than 7, excuse me, we can see that we would have 3 dots in that situation. So 3 divided by 100 is 0.03. 7 is going to be the most appropriate cutoff value. So at least statistically speaking, we would say in this situation that a value of 7 or less would indicate potential discrimination against women. If we move that cutoff up to 8, okay, so suppose we move that cutoff value up to 8 here, so right here at 8, if we say that 8 or anything less than 8 would suggest discrimination, okay, how many dots do I have down at 8 or anything less than 8? I would have 1, 2, 3, 4, 5, 6, 7. I have 100 dots. Okay, I have 100 repeated simulations here. So the 7 divided by 100 is going to be 0.07. Now that cutoff is a little bit too liberal. Likewise, the implication of using a cutoff that is too liberal would be that our model would too often indicate discrimination was taking place in situations in which it was not. So we'd be making a mistake there as well. Recall that most statisticians have agreed upon the 5% rule for an outlier. In using the 5% rule for outliers, we would want to use a cutoff value of 7 or anything less than 7. The percentage for 7 is at 3%, which is just slightly under that 5% level. So it is slightly conservative, but not too bad. We can actually use the reference distribution app to do these calculations for us. For example, I can place 7 in the as extreme as or less, down here in the lower left-hand corner in the as extreme as box. I can place 7 in there and click count, and it'll do the counting for me. So the dots that are at 7 or below than 7 are simply indicated with the red here. And as we computed by hand, there was 3 of those out of the 100. If we used 8 as a cutoff, okay, so if we put 8 in the as extreme as or less than box and click count, it'll count the number of dots that are at 7, or it'll count the number of dots that are 8 or anything less than 8. And the number of dots there is 7, which is 7%. If the goal is to use 5%, then using 7 is going to be the optimal cutoff value that we're going to want to use. The other thing that we could do is just simply look at how unlikely is the study outcome. To do that, recall that I know in our study, we had 9 women that were promoted. Okay, so if I placed 9 in the as extreme as or box and clicked count, what that's going to do is count the number of dots that are 9 or anything less than 9. And there's 12 dots in that situation. So the chance of seeing 9 or less women promoted under a no discrimination situation is going to be 12. Now, real quickly, when we're computing this probability or this chance, we actually want to look at 9 and anything less than 9. And the reason we do that is because if we believe that 9 is enough evidence for discrimination, then we're automatically saying that 8 is enough evidence for discrimination. And we're also automatically saying 7 is enough evidence for discrimination, and likewise 6. So when we're determining these probabilities or these likelihoods, these are being computed as 9 and anything less than 9. That's how that 12% was obtained. Let's just real quickly recap what we've learned here. The question of interest was, is there evidence of gender discrimination against females in this company for those chosen for a management position? The answer then, no. Statistically speaking, seeing only 9 women being promoted is not that unusual. Okay, it's not that unusual under a no discrimination situation. Our simulation model suggests that 7 or fewer women being promoted would be enough evidence to suggest possible discrimination was taking place. So from up above, our outlier rule identified 7 and below as being unusual. If no discrimination in a no discrimination situation, seeing 9 or less women being promoted happens about 12% of the time. And this 12% does not meet that widely accepted 5% threshold, thus suggesting that we do not have enough evidence for discrimination. Okay, let us consider next example 1.4.2. This is the ear infection example. A common symptom of ear infection in young children is the prolonged presence of fluid in the middle ear. There's been a hypothesis that has been proposed that babies who breastfeed for at least 1 month may build up some immunity against the effects of this condition. A small study of 24 babies is considered here. These babies were matched on a one-on-one basis according to age, sex, socioeconomic status, and types of medication taken. Okay, so these 24, there were actually 48 babies, but they were paired together into 24 pairs. One member of that matched pair was breastfed, and the other member of that matched pair was bottle fed. The question of interest here is the following. Is there a difference in the duration of ear infection between the breastfed and bottle-fed babies? Now, let's talk briefly about some study design issues. The idea of matching babies in this study is an important design consideration. Matching babies before conducting the study will permit us to make better comparisons in the study. For example, these babies were matched based on their age. Why that is important is because age is known to influence the rate of ear infection. Okay, so after about the age of 2 or 2.5, our ear canals get large enough that the rate of ear infections actually goes down. Also, when babies are brand new, the rate of ear infection is not very high, mostly because the babies have much of mom's have much of mom's antibodies to fight that infection. Sex was another variable that they considered in their matching criteria. The effect of sex on the rate of ear infection is not well established, but to be safe in this study, the children will be matched according to sex. Socioeconomic status. That is an important variable as well. In this study, socioeconomic status is synonymous with access and affordability of medical care. For example, how likely is it that if an ear infection comes up, that you can go to the doctor and get medical treatment? Okay, for some families, the affordability of medical care is higher than others. So socioeconomic status might actually impact the likelihood of an individual child having ear infection. Also, if a child is already on certain types of medications, we're going to want to take that into consideration. So if a child is on an antibiotic, then the rate of ear infection is going to be greatly reduced. So when they did the matching, They also looked at whether or not the child was on, for example, antibiotics. Some additional definitions here. The response variable. The response variable is the primary outcome or measurement of interest in an analysis. This is also known as the dependent variable or the Y variable. Now, for most of the examples that we've had up to this point, the response variable has simply been a count. For example, the count for the number of women that were promoted. The response variable here is going to be the duration of fluid in their inner ear. So we'll talk a little bit more about that in a minute. How about a confounding variable? What do we mean by a confounding variable? Maybe the best way to describe a confounding variable is through the context of this example here. Let us suppose that all of the breastfed babies were actually the younger babies, and all of the bottle-fed babies were the older babies in this study. Suppose in the end we find out that bottle-fed babies did better. Now, we don't know if it's because bottle feeding is better than breastfeeding, or is it because all the older children were put into the bottle-fed group. In this situation, age would be considered a confounding variable. And what we mean by a confounding variable is that it cannot be delineated from another variable when attempting to establish a relationship with the response. For example, I want to know whether or not I have a difference between breastfed and bottle feeding. Age might be considered a confounding variable in the situation that I just described. Likewise, if we put all the children that have a high socioeconomic status into one group, and all the children that have a low socioeconomic status in another group, we won't be able to identify, or we cannot be certain of the differences that we see in the end, if they're due to actually the feeding or if they're due to the socioeconomic status of the individual children. This matching that they did in a study prevents confounding variables. At least it prevents these confounding variables. If we match according to age, sex, socioeconomic status, and medications, then we know that those 4 variables anyway will not be confounding. Okay, the study outcomes. The primary outcome measurement for this study was the duration in days of fluid in the middle ear. What we're going to have to do in order to analyze this data using a 2 alternative forced choice method is turn these durations of fluid in the middle ear into a count. So how are we going to do that? The results of the 24 pairs of babies are provided here. So let us first look at pair number 1. Again, pair number 1 would be 2 children that would be of similar ages. They would be of the same sex. They would have similar socioeconomic status, and their medication levels would be similar. This first baby, okay, this breastfed baby here, so the baby that was breastfed in that pair had this fluid in its inner ear for 20 days. The bottle-fed baby had that infected fluid in its inner ear for 18 days. In this head-to-head comparison for pair number 1, the bottle-fed baby actually did better. And in fact, that baby did better by 2 days. Let's consider pair number 3. The bottle-fed baby for pair number 3 had fluid in its inner ear for 7 days, whereas the breastfed baby had fluid in its inner ear for only 3 days. In that head-to-head comparison, the breastfed baby won out. In fact, won out by about 4 days. As I just stated, in order to use the 2 alternative forced choice methodology for this example, we need to obtain the count for the number of times that breastfed babies did better and the number of times that bottle-fed babies did better. And what we need to do there is simply count up how often did the breastfed baby do better, and those have been highlighted here in yellow. So let's go ahead and do that. Looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So how often did the breastfed babies do better? That would be 16 times, it looks like. Oh, I apologize. That was breastfed, right? So let's go ahead and put that in the correct box. How often did the bottle-fed babies do better? The bottle-fed babies did better. It would be 1, 2, 3, 4, 5, 6, 7 times. That's what we would put there. And then how often did I tie? It looks like I had one instance of a tie. So for that tie situation, it looks like I had 7 days for the breastfed and also 7 days for the bottle-fed. Now we're going to have to deal with that tie here in a moment. We'll talk more about that in just a moment. Consider the following pamphlet on ear infections in children from the Department of Health from the state of New York. One interesting thing is that this pamphlet in no way is connected with the authors of our study, but they did make the following claim: that breastfeeding appears to lower an infant's risk of ear infections. Okay, when we get done with our analysis, we're going to come to almost the same conclusion there. All right, let's talk about that situation of the tie. In all of our analyses thus far, we have been restricted to only 2 outcomes. These are 2 forced choice, right? 2 alternative forced choice methods. We actually have 3 outcomes: breastfed doing better, bottle fed doing better, and a tie. Okay. As a result, one outcome must be eliminated if we're going to use this 2 alternative forced choice methodology. The pair that we're going to eliminate is pair number 8. Pair number 8 is a tie. What does this mean in the context of the problem? Well, this means that the number of days fluid was the same. Well, was the exact same. Does pair number 8 provide evidence for breastfeeding doing better, bottle feeding doing better, or neither? Well, the answer to that is neither, right? It's a tie, thus no difference. Between breastfed and bottle-fed kid. Baby, or this pair. If pair number 8 is removed, how many remaining pairs are going to be left in the study? So if removed, then go from 24 down to 23. Okay, next question. If there is no difference in the duration of ear infection between breastfed and bottle-fed, and we exclude the notion of a tie, how often should the breastfed baby do better, and how often should the bottle-fed baby do better? Okay, well, if there's no difference between those, under a no difference situation, about half the time, or about 50% of the time, breastfed should do better, and 50% of the time, bottle-fed baby should do better. So this example actually is going to be a 50-50 example. Let us now look at the simulation model. The schematic that for this simulation model is going to have the following features. Again, in the number line, we have our number line here. That number line is going to go from 0 up to 23. Okay, not 24 because I had to remove that tie. So 0 up to 23. Now, what I'm going to be keeping track of here is the number of times that breastfed wins. In our particular study, the study outcome that we had, remember that we had 16 times that breastfed won, 7 times that bottle fed won. What is the lowest possible value on this number line? Well, the lowest possible value on the number line is going to be 0. What is the highest possible value on our number line? The highest possible value on this number line is going to be 23. A typo there, but that should be 23. What would it mean if in every single situation the breastfed baby did better? So let's go back up here and look at the data that we actually obtained. So in other words, what would it mean if every single highlighted cell was here on the left side? Well, what that would mean is that the breastfed babies did better in each of those head-to-head comparisons. It did better in all 23 of those head-to-head comparisons. And under that situation, we would certainly claim that breastfeeding is better. And in fact, one should breastfeed their baby. So being really high on this number line is going to indicate that breastfeeding is better. Now, on the other hand, if we didn't have any breastfeeding wins, okay, so in other words, if we go back up and look at our table, if all of the highlighting was here on the right-hand side, okay, if all the highlighting was in the bottle-fed column, that would certainly indicate that bottle feeding is better. In that situation, we wouldn't have anything highlighted on the left side. So on our number line, if we end up being real small on that number line, that's going to indicate that bottle feeding is better. The center of the pyramid is going to be computed as 11.5. So the expected value here is going to be right around 11 or 12. When we're counting things, we can't actually have a half, but we don't worry too much about that. We just say that the expected value is right around 11 or 12. So what does that mean again? Well, the expected value being 11.5 is the number of times that we would expect breastfeeding to do better than bottle feeding in these head-to-head comparisons when there's no difference in the type of feeding. My study outcome here is going to be 16. Again, that's the number of times that breastfed won in our head-to-head comparisons for our data. Now the side of interest. This is our first situation where we actually care about both sides of the distribution. If the outcomes are too low, then bottle feeding is going to be better. On the other hand, if outcomes are too high, then breastfeeding is going to be better. In either case, the data would provide evidence for the research question. So when we're trying to determine the side of interest, we need to consider what side provides evidence for the research question. In this case, values being too high provide evidence for the research question, and in fact would suggest that breastfeeding is better. Also, values that are too low on this number line would suggest a difference exists, and in fact, bottle feeding would be better. So in this situation, we actually care about both sides of the distribution. This is often referred to as a two-sided investigation. Quick comment. When the question of interest contains the phrase, "Is there a difference?" then most likely both sides of the reference distribution are of interest. If you consider again the question of interest, For this problem, it starts out with, is there a difference in the duration, etc. Those first 4 words there are indicating that this is probably a two-sided problem in which interest lies in both sides. Let us quickly talk about the setup for the reference distribution app. The probability of a success here, which a success is being identified as breastfeeding doing better, is going to be set at 50%. The sample size is going to be 23, the number of head-to-head comparisons that are being done, with the tie removed. The number of samples here, I've set that to be a somewhat large value at 1,000. And again, a total of 1,000 repeated outcomes will be obtained in our simulation. If I were to ask about the 2 labels in this situation, they would simply be breastfed and bottle fed. Again, those are the 2 possible outcomes from the study. The reference distribution app, putting those quantities in, will let us obtain a distribution like the one presented here. The one additional note that I want to point out is that down here in the lower left-hand corner, there's a 2-sided button that can be selected. We're going to want this selected for this investigation here. Again, because I care about having values too high and also values too low. So doing a 2-sided problem, you're going to want to make sure and have that button selected down there in the lower left-hand corner. Let's talk about the application of the outlier rule. The application of the outlier rule will continue to deem 5% of the distribution as unlikely. In a 2-sided investigation, the unlikely values may come from either edge or either side of the distribution. When the 2-sided button is selected, the app will automatically consider both tails, as is shown here. So how do I determine the cutoff values? Suppose I believe 17 is kind of the edge of the distribution. I could simply put 17 in the as extreme as box and click count. Now, because I have the 2-sided button selected, it is going to count the values that are 17 and above, and it's going to count the corresponding values of 6 and below. If I use 16 and above, and the corresponding value of 7 below as my cutoffs, that is shown here at the bottom of page 37. Now, how does the computer determine the corresponding value on the lower side? Or how does the app determine that? Let us first consider using 17 and above. I've stated that the corresponding value here is 6 and below. The corresponding value is computed as follows. We know that the expected value, or the center of this distribution, is at 11.5. 17 sits 5.5 above 11.5. So if we take 17, subtract 11.5, we end up with 5.5. Now, we need to go that same distance to the lower tail. So I take 11.5 and subtract 5.5, and that's how the value of 6 is computed. So when we're looking at the corresponding value on the opposite end of the distribution, we need to worry about how far off are we from the expected value. One thing that we need to be careful about is that some people will use the edges to determine what the corresponding values are. So the maximum value on our number line, in this particular case, would be 23. 23 minus 17 is actually 6. That notion works, for some of the simple examples, but that is not always going to work. So what I'd rather have you do when thinking about the corresponding value is worry about how far away are you from the expected value. So in this case, again, I'm 5.5 above the expected value, so I need to go 5.5 below the expected value. Their corresponding values are 6 and 17 as stated here. If we use 16, okay, 16 subtract 11.5 is 4.5. So the corresponding value for 16 would be 11.5 minus 4.5, or 7. Now, when we use 6 and 17 as our cutoffs, we actually obtain 4% of the distribution. Okay, so 4% of the distribution would be identified as outliers. It appears that we have 17 dots below 6 down here, and we have 23 dots up here above 17. Those together are about 4% of the distribution. Remember, our goal is to obtain a 5%. So this looks like pretty reasonable cutoffs. If we move the cutoffs up to 16 and 7, we can see that the percentage of dots that would be deemed unlikely then would be 10.6%, which is a little bit above our 5% level. So the upper and lower cutoffs we're going to want to use in this case are going to be 17 and 6. Again, those two values give us a unlikely range, those two values using 17 and 6, okay, about 4% of the observations sit outside of that. And that's pretty close to the 5% rule. So let's go ahead and answer these questions on page 39. If the outcome from our study, which was 16 pairs for breastfeeding doing better, so is the outcome from our study an unlikely outcome under the situation of no difference? And the answer to that is not statistically speaking. The chance of seeing 16 or more and the corresponding and the corresponding 7 or less is about 10.6%. 10.6%. Okay. This does, well, we can say this maybe here. 16 is not in the unusual. 16 is not in the unusual. I can, or unlikely part of the reference distribution. Okay, so again, anything that's at 17 or above or 7 and below would be considered unlikely. And 16 is not quite in that unlikely part of the distribution. Okay, so 16 does not provide enough evidence of a difference. I'm getting ahead of myself a little bit here with this, but let's go ahead and much more than what was being asked in that question. How likely is it to observe a difference as large or even larger than 16? I guess we computed that, or I talked about that right up here. So the chance of seeing 16 or more, okay, the chance of seeing 16 or more and the corresponding value of 7 or less is about 10.6%. go ahead and put that answer where it belongs. Did we answer number 4 correctly up there? Is the outcome from our study an unlikely outcome? We just said 16 is not that unusual. All right. So suppose someone else decided to repeat this study, and they were actually careless and failed to match children before starting the study. So an important element of the study that was done here was the fact that those children were matched. We said that that would allow us to better make comparisons between the two types of feedings. Would it be easier or harder to establish a difference in feeding type in this study? So in a study where the matching was not done, it's actually going to be much harder. Okay, so if we don't take the time to do the matching, it's going to be much harder to be able to determine whether or not differences exist. So if a study, let's go ahead, we don't need to underline that. If a study does not use matching, it will be much harder to identify whether or not a difference exists in the types of feeding. The matching eliminated some of the potential confounding variables, which makes, the matching eliminated some of the potential confounding variables. Doing this will allow us to make better comparisons, better or more precise comparisons. So if a study does not do the matching, or if they do not take into consideration those potential confounding variables, it's going to be harder for them to make those comparisons. It's going to be harder for them to identify whether or not differences exist. So they are going to have less precision in their measurements, not more precision. Okay, let's recap the breastfeeding example. Is there evidence of a duration in ear infection between the breastfed and bottle-fed babies? Answer number 1, no. Statistically speaking, there's not enough evidence because 16 is not an outlier against this no difference pyramid. So in other words, 16 is within the no difference pyramid. Okay? Let me just for a moment though remove my statistician hat. I would agree that 16 is very close to that upper threshold for suggesting a difference between breastfed and bottle-fed. And in fact, it's up on the high side, which may suggest that breastfeeding is better. This study was not done on very many individuals. There were only 23 pairs of individuals that were being investigated here. With more and more data, or with more and more pairs, we might have more sensitivity in being able to identify whether a difference exists. In other words, with much more data, with many more pairs being considered, we might find that the study outcome is indeed in that outlier range and suggesting a difference between breastfeeding and bottle feeding. And if that's the case, we would actually agree with what was stated by the state of New York in their pamphlet regarding ear infection. If you remember, it was that breastfeeding appears to lower an infant's risk of ear infections. And I would support that statement. Even though we don't have enough statistical evidence to say that it's an outlier, it's pretty close. And the language that they used there was breastfeeding appears to lower an infant's risk. Okay, they're not saying for certain that it is, but they're careful in the language that they've selected here. Okay, that does it for section 1.4. We will get started with the next chapter, chapter 2, which is going to put a little bit more formality around we're going to get started with this next chapter, in which chapter 2 puts a little bit more formality around some of the things that we've been doing. Okay, thank you.